Hey, methods. We're up to 10C. Cool. Stationary points. This is exciting. Hey, oh yeah, in previous exercises we looked at calculating the gradient of tangent. Yep, which is cool. This one, what you need to know is, obviously a stationary point is when you get the gradient or differentiate, and at that particular point the gradient is equal to 0. So here are some samples as well. If you are looking at it visually, you can see here at this particular point at the maximum, at that point the gradient is 0. There's no slope there. Yep. Likewise here you can have a stationary point of inflection here. Again in the middle, 0 slope. Yep. So gradient is 0. Likewise at the minimum at this particular point, local minimum, it is derivative is 0 as well. So there's no slope. Cool. That's cool visually. Oh, it says here the reason we name it a stationary point becomes clear if we look at an application to the motion of particle. Yes, indeed, this one will help with where we get the name stationary point from. So in this particular case, we've got a particle is moving in a straight line. Perfect. Its position x meters relative to point 0 on a line at time t seconds is given by the following equation. Notice that they've restricted the domain for the time between 0 and 4. Yep. Alrighty, so it says find the particle's maximum distance from the origin, O, and hence the particle is always on the right of 0, or sorry, right of O, so the distance is from O is its position. Okay, cool. Rightio, so first thing we need to do is differentiate this equation here. So check, we can differentiate that. Perfect. We know that it's going to have a sort of a local maximum or a stationary point when we make this derivative equal to 0. Yep. So again, when we do that, if you were to factorize this, it's just difference of perfect squares. This is 3 squared take away t squared. You could solve this and find out that it's equal to 0. The derivative is equal to 0 at both t is equal to 3, time is 3, or time is negative 3. But we know that they're only looking between time being 0 and 4. So the negative value is not going to be the one that we're looking for. Yep. So what we need to do is we know that at time being equal to 3, there's going to be a stationary point. Yep. Up here. And what we can then do is, now that we know that that's the maximum, that's the stationary point or the turning point of the derivative, we can work out what is going on at time equals 3 by substituting that back into the original equation. Yep. So by substituting time equals 3 back into the equation here, we get that x is equal to 18. Yep. So again, it says the stationary point is at 318, and the maximum distance from O is 18 meters. Yep. So it travels 18 meters away from that O position. Obviously, this stationary point is where it stops moving, and obviously it starts traveling back towards the origin after that. Yep. It says here, note the stationary point occurs when the rate of change of the position with respect to time, that is, the velocity, is 0. At this moment, the particle is stationary. So at this particular point, it is stationary. Cool. Hence where we get the name stationary point from. Moving on, some of the other examples as well are asking you to calculate these stationary points. And they're all doing the same sort of thing. Yep. So you got the equation for A here. We need to differentiate that. Check. So we know the stationary point occurs when that derivative is equal to 0. So we're going to make the derivative equal to 0. Check. From here, it's a matter of solving that. Yep. So hopefully you can rearrange that and work out what x is. X is equal to 3. Perfect. So that means a stationary point is going to occur in this equation when x is equal to 3. What we need to do is substitute in x equals 3 into the original equation and find out what its corresponding y value is. So again, when we substitute 3 into the equation, we get 27. So we can find out that the stationary point occurs at 327. Cool. Here with B, again, first thing is we need to differentiate it. Once we differentiate it, we make it equal to 0, because that's when a stationary point occurs. So here we've differentiated it perfect. They've factorized this as well by taking out common factor of 3. So when by taking out the common factor of 3, it just leaves you, I'll draw with my little tool here, hopefully this works. Taking out 3 as a common factor, it just means we can solve this part here. 1 take away x squared is the same as 1 squared take away x squared, which is a difference of perfect squares. So solving that tells us that x can be both positive and negative 1. Yep, equaling 0. Obviously that doesn't mean anything there, the 3. So once we know that the solutions, possible solutions for the stationary point are positive 1 and negative 1, we need to substitute both of those back into the original equation and find out its corresponding y coordinate, which is easy enough to do. You get the stationary points, which is multiple, happen at 1, 6, and also at negative 1, 2, by substituting those back in here. Happy days, cool. This one here, we've got an equation. Perfect. Again, with each of these, we need to get the derivative. Cool, we've got the derivative in this particular case. Again, note the restriction on the domain. Time has to be greater than, I'm assuming it's time. T has to be greater than 0. So make the derivative equal to 0. They've taken out a common factor of 2. Bang, it comes out the front. You're left with this quadratic. We can simplify or factorize this quadratic. This quadratic factorizes as follows. We can then solve this quadratic equation to find out when it equals 0. Now, obviously, in this particular case, making this equal to 0 rearranges to t equals negative a third, and this one here is t is positive 2. Again, because there was a restriction on the domain, you're only after the solution where t is greater than 0, so that's this one that we're going to be choosing. Given now we know that the stationary point occurs at t equals 2, substitute that back into the original equation and you'll get the corresponding stationary point, which is 2, 1. Perfect. Oh, cool. You can do stationary points with other types of functions as well. Same difference. All you're going to do is find the derivative, make it equal to 0, and then find where those stationary points occur by substituting it back into the original equation. Yep. So here, this one, sine 2x, we can differentiate that. Happy days. Make the derivative equal to 0. You might have to think back to how we go about doing these things. In this particular case, there are 4 solutions here. Yep. In this particular case, again, because it's between 0 and 2 pi, we're going to substitute these back into the original equation to find their corresponding y coordinates, which are listed there. These are each a stationary point. Perfect. This one here, y equals e to the power of 2x take away x. Again, differentiate, make the derivative equal to 0. Yep. Rearrange things. In this particular case, we find out when that occurs. Negative half log to the base e of 2. So substituting that back into the original equation, you get the original, the coordinates of that stationary point. Yeah, it looks worse than it actually is, but again, we understand this type of stuff. This one here, stationary points of x log e of 2x, it's between 0 and infinity. Again, differentiate. Yep, you might have to think back of how we do differentiate different things, some of the skills we've learned recently, and make the derivative equal to 0. Solve that. Here's going to be where the stationary point occurs. You substitute that back into the original equation to find its corresponding y coordinate. Yep. Alrighty. Oh, this one's, I like this one. Yep. Like I like all maths. Yep. Example number 14. We've got a curve with an equation here. They're giving us some information. They're telling us it passes through the point 0, 5. So we can use that to get some additional information. And it also has a stationary point at 2, 7. Cool. So it says find A, B, and C. Rightio. So if we plug the x and y values, we draw a y. Imagine that says y. Yep, x and y values into the original equation. So you put 5 here, 0 cubed plus a 0, that's 0 plus 0 equals c. You'd get, ultimately, that 5 is equal to c. Yep, so you get the c value by plugging those two values into the original equation. Next, this stationary point occurs when the derivative of this here is equal to 0. So again, we can get the derivative of this, which is 3x squared plus 2ax plus b. And at the point when x equals 2, because here it's telling us at this particular point it's a stationary point, when x equals 2, you know the derivative is going to be equal to 0. Yep, it's a stationary point. So we can create an equation based on this. Yep. So plugging in x equals 2 and making it equal to 0 will give you one of the equations. The other piece of information we know is that we've got the point 27 is also on the curve. So again, you can plug these values here into the equation and it will generate the second equation. Once you have 2 points, happy days, you can use our fun simultaneous equations, whether you are doing substitution or elimination. It's up to you on your calculator if you have access to it. Ultimately, you can use that to get both the a and b values. Yep. In this particular case, they have used the elimination method by subtracting equation number 1 from equation number 2. And they have got the values of a being equal to -9/2 and b equal to 6. And also, I guess we did work out that c was equal to 5 earlier on. Alrighty, happy days. I think that's it in terms of worked examples. As always, you might choose to have a bit of a play around with your CAS calculator on this. Actually, as it says here, you can define each of these equations. So this was the one from example number 14. So they've defined f of x as the original equation. They've defined g of x as the derivative of f of x, and then what they've actually said here, they've put in the information from the question as well. They've said when we substituted 0 into f of x, it was equal to 5. Yep. They've also put in the information about the stationary point occurring at 2, 7 from the original equation, and also saying that the derivative when it's at 2 it's a stationary point, so it's equal to 0. From there, it's saying, hey, can you solve A, B, and C? And you can do it with your CAS calculator that way as well. So it's worthwhile checking that out. That is the way you could do that one on your CAS calculator for example number 14. Cool. Thank you very much for listening up. Have fun with exercise 10C today. Bye for now.